Okay, in this podcast, I'm going to review bonding and intermolecular forces, and in another podcast, I'll review gases. A little too much for one video, I think, so we're going to do them separately. Okay, so let me just get a red pointer up here. All right, if we think about the energetics of really anything, this is a sort of a fundamental idea that's really important. Anytime I have a situation where I am separating two things, I could be breaking a bond, I could be removing an electron from an atom. Anytime I'm separating things, I could be just separating waters that are hydrogen bonded to each other, right? Breaking an IMF. That always requires energy. It's always endothermic. I cannot do that without some energy input. Okay? Anytime I am bringing things together, because they're attracted, they come together, so I could be adding an electron to an atom, I could be forming a bond, I could be creating or joining things based on IMFs. Anytime I bring things together, the only reason for them to come together is to become more stable. And when I say more stable, I mean lower in energy. So this is always going to be exothermic. Bringing things together is always exothermic. And things won't come together unless they're more stable or lower in energy, which means they're going to release energy. So for instance, sodium and chlorine, you don't mine sodium, you mine sodium chloride. Sodium is unstable as an atom. It is more stable within a compound. So the formation of that must be exothermic. But if we look at the separate events, the separate parts of that, the sodium atom that has 11 protons and 11 electrons, losing an electron, we saw in the last podcast that takes 495 kilojoules of energy to do. And if we look at chlorine and looked at the 17 protons, 17 electrons, and gaining an electron, we said that has an electron affinity. I'm adding an electron here, so I am releasing energy. I'm releasing 349. But if I were to add those up, I would get, I would get a net positive or an endothermic reaction. But if you were to watch the formation of sodium chloride, look at that. That is, you can see the heat. You can see that it is exothermic. Okay, it's generating lots of heat. So why is it so exothermic if the formation, if I sum up the two steps, sodium losing an electron and chlorine gaining an electron, why is it so exothermic? What's the other piece? Well, the other piece is lattice energy. So if I think about it, what happens once that sodium has lost an electron is it becomes positively charged, and the chloride becomes negatively charged. And because the charges are opposite, they are attracted to each other and they come together. This coming together, this lattice formation, is exothermic. The coming together is exothermic, and we call that the lattice energy. Now, lattice energy is actually defined as the energy required to separate this crystal lattice with positives and negatives, very strong structure, separate it into gaseous ions. Okay, so the energy required to do that is the same as the energy that gets released when it forms. Okay, so the energy associated with breaking a bond is the same as the energy associated with the formation of that bond. They are just opposite in size. In sign, right? So lattice energy, this coming together of the positive and negative, releases a lot of energy. Okay. So we can look at lattice energy and understand what the trends are. If I look here, I've got all of these are group 1 metals with halogens. Okay, so they're all +1, -1s. But if I look here, I've got +2 ions, minus 1, plus 2, minus 2, plus 3, minus 3 ions. And what I see is I go from plus 1 to minus 1 ions to plus 2, minus 2, plus 2, minus 2, that my energy, my lattice energy goes up, which means that this is a stronger crystal. It's harder to separate it. There is stronger attraction than there is here. Okay. So lattice energy increases with the charge of the ions. Okay. And we will also see that it changes with the size of the ion. So as we go from very small atoms, we have higher energy than we do when we get to larger atoms. Okay, so as we get larger anions, the energy is lower. So these smaller guys have stronger lattice energies than the bigger ions. Okay, and that's because of Coulomb's law. So Coulomb's law can be explained by, so this is the force of attraction is equal to some constant times Q1, Q2. So let's say I had a positively charged object and a negatively charged object. They're going to be attracted to each other, right? Actually, the arrows are going to come in. They're going to be attracted to each other and come together. If I had a positive 2 and a negative 1, they're going to be more attracted than the plus 1, minus 1. If I had a big positive over here and a big negative, they're going to be very attracted, even stronger attraction. That's what Q1 and Q2 is. You can think about this as the positive charge and think about this as a negative charge. The other piece of this is the denominator. So if I think about, I have a positive charge that's very close to the negative charge, we're going to feel that attraction stronger. Think about putting a magnet onto something that's magnetic. The closer you are to it, the more that magnet pulls towards that object. But if I separate that magnet a distance from the opposite charge, it feels very little attraction, and to the point where it reaches a point where it doesn't feel any attraction. So the smaller the substance, right, the smaller the d, the larger the force of attraction. And what we'll see is that when we're looking at lattice energy and comparing, that what matters the most is the charge. But if I have the same charge, plus 1, minus 1 on my ions, then I need to look at the effect of the distance or the size of the ion. So if I'm looking at these, what I have here is plus 1, minus 1, plus 1, minus 1, plus 2, minus 2. So this is going to be the strongest, the highest lattice energy, right? And then I have these two. So sodium fluoride are small ions, cesium and iodide are large ions. So this is going to be the second strongest, and this would be the weakest, right? Because the proton in the center, the protons in the center, and the electrons out here are further away and don't feel that pull as greatly. Here I have plus 2, minus 1, plus 2, minus 1, plus 2, plus 4, minus 2. Okay, so definitely this is going to have the strongest lattice energy, or the highest. It's going to have a high lattice energy. These are going to be smaller, and because magnesium is smaller, a smaller ion than calcium, the magnesium is going to have a higher, magnesium fluoride will have a higher lattice energy. Okay. When we think about covalent bonding, what you have to think about is that there are attractions between electrons and nuclei. So let's say I have let's say this is a hydrogen atom and this is a chlorine atom. And the hydrogen has electrons, and those electrons on the hydrogen are not only attracted to the hydrogen atom, but they are also attracted to the chlorine nucleus. Okay? So one atom's nucleus is attracted to the other atom's electrons. there's also repulsions between electrons. I'm just going to abbreviate it like that. So as I have two atoms represented down here coming together, I have these electrons that are going to repel each other, right? These electrons, as I was showing, are attracted to this nucleus to those electrons, okay? And we also have repulsions between nuclei. So if these atoms got too close, now I have this the positive nucleus and the positive nucleus of the other atom start to repel each other and push each other away. And as a result, what you get is this chart. That's a very important chart that comes up a lot in the AP test. On the left axis, the y-axis, we have potential energy. On the x-axis, we have a distance. So think about this. I have two hydrogen atoms, okay? If they're far enough apart, they don't feel any attraction. But as they get closer and closer together, they reach a point where suddenly they have this drop in energy. And that place where the energy is at a minimum is where the bond forms. So this bond forms at a point where this is my bond length. I can measure it, right? Read it off the graph. And this is my bond energy, is this distance from 0 to the potential energy. And this is going to be a negative, right? This is going to be 0 potential energy. This is going to be negative, right? Because things are coming together, and those electrons are going to be, those atoms are going to be attracted, and they're going to combine, and they're going to release energy. If these atoms got too close together, I have the overlap in the atoms, and these nuclei repel each other and push each other away. So there's this sweet spot right here where the bond forms, and this distance is the bond distance, or the bond length, and this energy is the bond energy. Okay, so we can look at polar covalent bonds, and what polar covalent bonds mean is that if I have two atoms that are bonded together and they're sharing a pair of electrons, that those electrons are not shared equally. So I can look at an electron density cloud. There's more electron density, more negative and more positive on this side. The electrons are more dense over here, so the fluorine is holding those electrons more closely than the hydrogen. And so I can see the difference in electron density is greater in HF than it is with HCl, and then HI has the very least. And what you'll see is the greater the difference in electronegativity between the two atoms, the more there's a shift in the electron density. And I form what's known as a dipole. And that dipole means that one side is more negative and the other side is less negative or more positive. Now this is not a full negative and a full positive. It's not an ion. It's a partial. Okay, one side is more negative, one side is more positive. And if I add those dipoles together, I get a dipole moment. I can actually put a vector on it and point the arrow towards the more negative side. Okay, so if I wanted to compare polarities, or which bond is more polar, I can compare electronegativity values. So if I look at the difference between boron and chlorine 2 versus 3, that's an electronegativity difference of 1. Carbon versus chlorine is 3 and 3. So this is essentially 2.5 versus 3. So this is 0.5. This is a 1. So this is going to be a more polar bond. Difference between P and F. What I know is F is the most electronegative element on the periodic table. So it is going to, the difference between it and something else is going to be greater than any other thing in that same other thing. So this is going to be more polar. And you can see that if you looked at the numbers. I don't plan to go over how to draw Lewis structures. If you need help with that, see me individually. But my best advice to you when you get asked about shapes or molecular polarities is you have to draw the Lewis structures. You know, I've been doing this a long time and I still draw the Lewis structures. You got to draw the Lewis structures to get the shapes right. The other thing I'll tell you, a big hint, is that if you're doing your Lewis structures and you're trying to decide where you need single, double, and triple bonds, the only atoms that form double bonds are CNOPs: carbon, nitrogen, oxygen, phosphorus, and sulfur. So if you're given choices about structures and you have a multiple bond involving a halogen, that is not a legitimate structure, okay? CNOPs, these are the elements that can form multiple bonds. Okay, resonance, so here's the idea with resonance. If I were to draw the Lewis structure for ozone, O3, this is what I end up with. I could put the double bond here, or I could put the double bond here. And in fact, what the evidence shows us is this bond and this bond are the same distance, okay? Which means that they are equivalent to each other. So you could think about this like I have a 1.5 bond, that these two bonds are averaged, that I don't have a double bond and a single bond, that these two are the average of each other, and they are identical. So if I think about benzene, which is a popular structure that comes up, benzene C6H6, it's a ring structure. It's called aromatic because it's a ring. And I have alternating double and single bonds between the carbons. And if you look at what we believe that shape really is you have this area of delocalized electrons above and below the ring of carbons. And you often will see benzene shorthand drawn like this with a circle in the middle, indicating that all the bonds are the same. So, delocalized electrons in a ring. So you might get asked a question like this: which is predicted to have shorter sulfur-oxygen bonds? So if I have SO3, I have 6 electrons here, I have 18 here. Let me see. So that's 8, 16, 6 times 3 is 18, plus 6 is 24. 8, 16, 24. So this is good. I don't actually need this. There's no lone pair there, so ignore that, okay? So this is what I have. If I have SO3 minus 2, I have 2 more electrons. So what I end up with there is this, okay? So what I have here is 1 double and 2 single. Here I have 3 single, okay? So which has the shorter bond? This does. Because the average here, I have a double, and I have 2 times 1 is 2 singles, so I have a total of 4, and there's 3 bonds, so they each have a bond 4/3, so they have a bond order of 4/3, or 1 1/3. One of the things you might get asked about is using formal charges. Sometimes we can draw the same, we can draw legitimate Lewis structures 2 different ways for a compound. For instance, if you were drawing the Lewis structure for carbon dioxide, you could draw it with 2 double bonds, or you could draw it with a single bond and a triple bond. And when that happens, we can use formal charges to determine which of those structures is preferred. So the way that it works is I take a look at oxygen and I say how many valence electrons does oxygen have. It has 6, this has 6, this carbon has 4. And then I look at how many electrons are assigned to it in the structure. So it would be 1, 2, 1 of each of these, 3, 4, 5, 6. Okay. Carbon is assigned 1, 2, 3, 4. and this oxygen is 1, 2, 3, 4, 5, 6. So my formal charge here is 0, 0, 0. Here, this oxygen brings 6, so does this. This carbon brings 4. 1, 2, 3, 4, 5, 6, 7. Okay? The carbon is associated with 4, 1, 2, 3, 4. And this oxygen is associated 1, 2, 3, 4, 5. So what I end up with is a negative charge here and a positive charge here. The best situation to end up with a formal charge standpoint is they're all 0. So this is the preferred structure. So the best Lewis structure is, from a formal charge standpoint, is the one with the least charges, right? So if there's 0, perfect, okay? If there's not 0, let's say I have an ion, I'm always going to have a negative 1. What I want to look for is that I have the least charges first of all, so this is not going to be a good choice. It's going to be one of these. And this second thing I want to look at is that the element that has the negative is the most electronegative element. And as it turns out, nitrogen is more electronegative than oxygen. And so the negative charge should be on the nitrogen, and therefore this is the preferred structure. Okay, there are 3 types of exceptions to the octet rule. Let's take a look at each of them. The first is you end up with odd numbers of electrons. And usually when you do this, you're talking about some involvement with nitrogen. And these are very, very unstable. They're called free radicals because they have this unpaired electron. They react with something else pretty easily. But they do exist. Okay, that's an exception to the octet rule. You also have situations where you have fewer than 8 electrons. And if you were to look at the formal charges, you would see that the preferred structure for something that has boron in it is that boron ends up only with 6 valence electrons instead of 8. And so you see this with very small atoms. And the examples that might be on the test are almost always with boron. Boron will end up with 6 electrons around it in a Lewis structure. And sometimes with beryllium. That can be involved with covalent bonds, and it'll end up with just 4 electrons. Okay, that's a legitimate structure. You see a lot of structures that have more than 8 electrons, but it can only happen in large atoms. And by large atoms, I mean period 3 or below. Okay, so they have to be large enough to fit more than 8 electrons around here. In this case, we've got 10 electrons around the phosphorus. Very common. And the general idea is that the reason it's going to be the 3rd period and below is because you need to have d electrons available, because apparently there's some involvement with d orbitals in forming these bonds. Okay, and of course you need to be big enough to handle all of these atoms around here. So it's got to be the 3rd period and below. Okay, so it can't happen in period 2 or period 1. Those atoms are not large enough and they don't have d electrons. Okay, so if we looked at the covalent bond strength, we can define bond strength as the bond required to break a bond and leave you with gaseous atoms. Okay, so we can look up the bond enthalpy. We call this enthalpy. The delta H for the Cl-Cl bond is 242 kilojoules. So that's the energy required to break this. Okay, it's also the energy that gets released if I go this way, right? It's the same 242 kilojoules, but in this case I'm going to be releasing it if I am forming the bond. So as I look at these average bond enthalpies, these are listed as positive values. So that means this is the energy when that bond is formed. If I am breaking the bond, it is going to be energy required. Okay, if I'm forming the bond, it's going to be energy released. Okay, so energy must be used to break a bond. I cannot break a bond without energy input. So, well, let's take a look at some of the trends. So one of the things we should notice is that here I have all single bonds. Here I have double and triple. And what you'll notice is that the triple bonds have a greater bond energy than double, which has greater than single. So the more electron density in the bond, the higher the bond energy. Okay. The other thing that you'll see is that the greater the electronegativity difference between the atoms. So if I look at something like, let me see. So things with same electronegativity are going to have low values, right? A non-polar bond, whereas something with a big difference in electronegativity are going to have large bond energies. Okay, so this is based on difference between the atoms and electronegativity. Okay. All right, so we're going to talk about enthalpy in Unit 5, but the enthalpy for a reaction when we're using bond energies is important, and it's calculated a little bit differently. When I am looking at the overall enthalpy for a reaction, I have to look at the energy required to break bonds. And because I'm breaking bonds, that's a positive energy, right? I got to apply that energy to make that bonds break. And then when I form these bonds, I release energy. So that is going to be energy released to form bonds. So this is positive, this is negative. I add them together, and that gives me my delta H. Okay? So if I'm asked what is the bond energy, or what is the enthalpy of this reaction, what I have to do is draw the Lewis structures. And I recommend you draw the Lewis structures. You might think this is kind of simple, because one of the things you'll realize is sometimes they'll throw in a double bond or a triple bond. Like if you didn't draw nitrogen, you might forget that it's a triple bond, and you might have a table of bond energies and use the wrong ones. And here I'm making 2HF. So this is going to be positive energy. H2 is 436 plus 1F2, which is 158, right? And I'm going to get out the energy from the formation of the bonds. So I'm going to have 2 HFs. And all of this, I added up, it's going to give me my delta H. Okay, sometimes you'll, so the stronger the bond, the shorter the bond. Okay, so these triple bonds, much shorter than the double and much shorter than the single bond. Okay, so this term bond order might get used. If I have a double bond, it's a bond order of 2. If I have a single bond, it's a bond order of 1. And if I have a triple bond, I bet you can figure this one out. It's going to be a bond order of 3. But here I have a double bond and a single bond. So this has a bond order of 2. This has a bond order of 1. So my bond order for ozone is 1.5, because remember, it's the average of these two. Okay. So as the number of bonds between two atoms increases, the bond length decreases, right? They come closer together. All right. Metallic bonding, what you want to talk about here is the sea of electrons, of mobile electrons. So a lot of the properties of metals can be attributed to this sea of mobile electrons. So the way a metal, if you think about a sheet of iron, for instance, I have essentially the nucleus, or you can think about these like cations, and they are surrounded by the electrons, but their valence electrons are mobile. They are delocalized. I'm having trouble here today. Delocalized. So they can easily move in a direction that they are induced to move. So if I put a positive electrode here and a negative electrode here, these electrons are going to shift towards the positive. So they are free to move, and because they're free to move, they will conduct electricity. And because they're free to move, if I hammer them to determine whether or not they're malleable, they just move when the atom moves. So they're quite flexible. Okay, so I can explain a lot of the properties. They're conductive because the electrons are mobile. They're malleable because I can hammer them and those electrons will move. Ductile is the same kind of thing. Drawing them into a wire, those electrons will move. And they're low volatility. You know, they're a pretty strong structure based on the delocalization of the electrons surrounding multiple cations. Let's just talk about alloys a little bit. Alloys, there are two types, and they are, so this is a mixture, not a compound, but a mixture of metals. And generally, alloys are used to get better performance than you can get with one metal by itself. So this is an interstitial alloy. I have mostly iron, but I have little bits of carbon, smaller atoms than the iron, that fill some of the gaps. So something like this could make this this metal more rigid. Okay, it provides some other properties. This is actually what carbon steel would be. Okay, it's an alloy of iron and carbon. This is a substitutional alloy, which means if I have this copper sheet, I am replacing some of the copper atoms with another element, another metal that has an atom that's similar in size. Okay. Covalent network solids are solids that you have that they will actually bond with themselves. So for instance, if I have this carbon has 4 electrons, so it easily bonds with itself. And when it does that, carbon examples are the most common. They form some pretty strong structures. I can form graphite, which is, you could argue, not very strong. And the thing about graphite is it forms these sheets. We call these allotropes of carbon. They are all the same elements, but because they will bond with itself in different ways, they form actually substances with different properties, so they're allotropes. You may have heard about the nanotechnology associated with buckyballs, where the carbon is in graphite it's a two-dimensional bonding. In buckyballs or in carbon nanotubes, they are bonded in 3 dimensions, which makes them extremely strong. Very, very good mechanical properties. Okay, so those are covalent network solids. You can also have molecular solids. So an example of a molecular solid might be glucose, right? A large molecular compound, okay? And it could be polar or non-polar, okay? There's probably some polarity if it's a solid at room temperature. Otherwise, it would be a liquid at room temperature. It would melt, okay? All right, so let's take a quick look at molecular geometries. So molecular geometry is based on this idea of valence, what we call VESP, or valence shell electron pair repulsion theory. Okay, sounds like a mouthful, but the whole idea is if I draw a Lewis structure and I look at how many places around the central atom I have electrons, I can determine the shape. Because the idea is that these electrons are going to be evenly spaced out in three-dimensional space to be as far apart from each other because they repel each other. They're negative on negative. And based on that, I can look at what would happen if I have four things equally spaced around a center. And what I get is this tetrahedron. Tetrahedral. And if you looked at the angles for those, it would be 109.5. Okay. So there are 5 of what we call electron domain geometries. And when I say electron domains, we're looking at around a central atom, how many places are there electrons. And it doesn't matter whether they are in a bond or they are lone pairs. This has a 4 electron domain geometry. Okay? And I would also have a 4 electron domain geometry if I had just this. Okay? So we're going to take a look at each of these 4. Okay, so you will often get asked for electron domain geometry, and you could be asked for molecular geometry. They are different. Okay, so for instance, water, if I drew the Lewis structure, okay, this I could say is my electron domain geometry. I have 4 domains, 1, 2, 3, 4. And if they were equally spaced out, like we just said, that'd be a tetrahedral electron geometry, right? Just like NH3's is. NH3 is the same, but it has just 1 lone pair. This has 3 hydrogens instead of the 2. Okay, molecular geometry refers to the same Lewis structure, but the only thing that gets included are bonded atoms. Okay, there's a lone pair up here, but you don't see them. However, they do influence the shape because they push away, according to Vesper theory, and cause this to form a sort of pyramid. Okay, which is why the molecular geometry is trigonal pyramidal. So within each electron domain geometry, let's say the tetrahedral electron domain geometry, there are 3 different molecular geometries. These large purple things represent lone pairs. These are bonded atoms. So if I have a bonded atom at each of those electron domains, I have a tetrahedral molecular geometry. If I have 1 lone pair and only 3 things bonded, I have a trigonal pyramidal. And in the case of water, if I have 2 things bonded and I have 2 lone pairs, I still have 4 electron domains, then I'm going to have a shape that's bent. Okay, so I think we understand these geometries pretty well. What's new for us this year are the electron domains that go beyond 4. Okay, so let's talk about this is a 5 electron domains. Okay, and so if I think about it, so here's the central atom, and it's got 1, 2, 3, 4, 5 electron domains around it. Okay, and if I think about this, there are I can think about 2 distinct positions. I can think about this like an equator going around the sun. So there's equatorial, and I can think about those like arms, right? My arms, and then I have axial positions. They form a line, and I have a head and a foot. So these are axial. Okay. So if I have a trigonal bipyramidal, that is the electron domain geometry for all of these, right? Because it's got 5 places with electrons. And if they are all have atoms on them that are bonded, then my molecular geometry is also trigonal bipyramidal. Okay? Now, if I replaced, I can live without an arm, but I can't live without a head or a foot. So I always take off from the equatorial first. Okay? That's how I think about it. So if I took away one of these atoms, the electrons still influence the shape, and if you were to build that, what you could see is that you have a seesaw. Okay? These would be on the ground, and this would be going up and down. So this is a seesaw shape. Okay? Here I have, these are 2 lone pairs. I don't see them. I see the influence that they have on the bond angles. So this is my structure, and as you can see, that's a T-shaped. And if I lost all of my arms or all of my equatorial positions, and I just have a bond on the axials, then I have a linear shape. Okay. The last is the 6 electron domain geometries, and that's called an octahedral. Okay, if I have bonded atoms on all of those, I have an octahedron. Okay, and thinking again about depending on how you line this up, you could consider any of these to be equatorial or axial. Okay, so if I take off one bonded atom, I still have the electrons. So what I'm going to end up with is something called a square pyramid. If I lay it down, these 4 atoms are going to lay on the table, and this is going to be sticking up. So I have a square base that forms a pyramid. If I remove 2, I'm going to most likely remove them across from each other. We always are looking for symmetry, and I'm going to end up with 4 bonded atoms, and they are going to form a square that lies flat on the domain. Okay. Okay, if we have large molecules, generally you're going to be asked, what is the geometry around a specific atom? In this case, I have a functional group that's going to be where the molecule is likely to react. So I could be asked, what is the molecular geometry around here or here? So the answer would be different depending on which carbon you look at. Okay. Okay, and one of the things we have to be careful about is the difference between bond polarity and molecular polarity. So if I think about the carbon dioxide molecule, the carbon-oxygen bond is polar. The oxygen is more electronegative. This is more electropositive. Okay. This is more electronegative. Okay. So this is polar, and this is polar. And if I were to draw a dipole, and if I were to draw the dipole, I point towards a more negative side, put a slash here, and this forms a positive, right? What happens is this dipole cancels out. It's equal and opposite, cancels out this dipole. And I end up with an overall dipole moment, and the moment is the size of the dipole, of 0. So this side of the molecule is just as electronegative as this side of the molecule, and I end up with a non-polar molecule that has polar bonds. Okay? So if I'm thinking about whether or not a molecule is polar, I have to look at what happens when I add the dipoles. So here, water, H and O are polar bonds. The dipole moment points up this way. If I add those together, I end up with quite negative here and quite positive here. Not full negative and positive, okay? So very high electron density up where the oxygen is. So when you're asked why a molecule is polar, it's always because if you add the dipoles, you have a net dipole moment. If it cancels out, then you are nonpolar. So in order to determine whether a molecule is polar, I have to draw the dipoles for each of the bonds and see whether or not they cancel each other out. So in the case of carbon tetrachloride, they cancel each other out. But if I replaced 3 of those with a hydrogen and one has a chlorine, now they don't cancel out, right? Now I've got one side of the molecule that's more negative and one that's more positive. All right, the last thing we're going to talk about here is hybridization. If I think about carbon with 4 hydrogens around it, I draw it like this and it looks like all those bonds are the same. But are they the same? If I think about it, this is the orbital notation for carbon's last 4 electrons. So they have 2 2s electrons and a 2p electron in each of 2 different p orbitals. And you look at that and say, well, should they really be identical if in fact they are coming from different parts of or different shaped orbitals? And the answer is, in fact, they are all identical. Okay? What I have is a hybrid of all of these. So I get some averaging of the bonds. And those averagings are called hybrid orbitals. Okay? So once you know the number of electron domains around a central atom, that will give you the hybridization. So if I have 2 electron domains, I'm going to have sp hybridization. Because I can think about there is a 1 here and there's a 1 here. And if I add those together, I get a 2. And that 2 is the 2 electron domains. If I look at 4 electron domains, I can only have 1 s. I can multiple 3. They have to add up to 4 for the electron domains. If that's a 1, that is a 3, and I have sp3 hybridization. Not surprisingly here, I have I have 3 electron domains. It must add up to 3, so I must have p2. Pretty simple. That's really about all you get asked. We also can look at this idea of sigma or pi bonds. It's another way of looking at how these bonds form. If I have a single bond, I have what's known as a single bond, which means I have a head-to-head overlap. I can also have pi bonds, and pi bonds involved a side-to-side, more complicated overlap. The only thing you get asked on these, though, is based on some structure, how many sigma bonds, how many pi bonds. If I have a single bond, I have 1 sigma bond. A single bond is always just 1 sigma bond. If I have a double bond or a triple bond, the first of those is a sigma, okay? And any subsequent one is a pi. So if I have a triple bond, I have 1 sigma and I have 2 pi's. Okay? That's really all you need to know for that. Okay, sigma bonds by themselves are stronger than pi. They're stronger than pi. But double bonds are stronger than single bonds because I have both a sigma and a pi. All right, we're going to stop there and do IMFs as a separate podcast.